Good morning. It's a pleasure to be in Santa Cruz. I spent 2 years here and it was fantastic. One of my kids was born in Santa Cruz. He said he wanted to come back and he said, "Why did you leave? Why did you come back to France?" He likes skateboarding. So I will speak not about skateboarding, but about star formation in galaxies. And we know that star formation is a local process taking place at scales of the order of the parsec. But the question I would like to address today is how sensitive is star formation to larger scales, either inside galaxies at the kiloparsec scale or even outside megaparsec scales. The key to understand that is really to be able to measure star formation independently of dust obscuration, and that's why accessing the far infrared emission of galaxies thanks to the Herschel satellite is going to be crucial to see the emission of young and massive stars and then study the short time scale of star formation. The key questions are connected to the stochasticity of star formation, the continuous versus stochastic star formation events, what's the role of mergers in star formation, and what I would like to convey is the idea that we are now in a situation where we can start to really bridge the megaparsec and subparsec scales from observations, and I'm seeing also that from simulations, and I won't speak about simulations, but for example, Frederick Bono in our institute with his students and postdocs have been able to make simulations at subparsec scales, which are very much converging with to the same kind of results that we are observing. So the title of this talk is Searching for the Dominant Mode of Galaxy Growth from the Deep Herschel Extragalactic Surveys. The Spitzer view we had on the cosmic star formation history a few years ago is given here from the Lefloc et al. Paper in 2005, where you see a rapid rise of the lurgs and U-lurgs, those galaxies which emit vast majority of their light in the far infrared and which are dominantly triggered by mergers. The fact that they are rising so fast makes us think that mergers are going to play a key role in triggering star formation in a distant universe. Another issue, an issue which came out of the Spitzer results, is the fact that when you try to compare the star formation rate you get from the mid-infrared to the ones you would get from the radio, UV corrected for extinction, or stacking in the far infrared, because Spitzer was not had a resolution, good enough resolution to see the far infrared emission of individual galaxies, you would see that there was a so-called mid-infrared excess problem. That means you would overestimate the star formation rates of galaxies. With Herschel, we can now really probe the far infrared emission in the race frame of the galaxies up to very high redshifts, and I'm showing here the latest result by Magnelli et al. Combining the good Herschel and PEP data sets, showing you the evolution of the cosmic star formation rate history. And if you compare that to the one we had with Spitzer that you see here, you see that they are very consistent, and the rise of U-lurgs continues up to redshift 2, while the lurgs remain relatively flat. So that suggests that really those galaxies which are affected by mergers may play a key role, but how representative is the cosmic star formation rate history of what happens in individual galaxies? That's the question. Now, if you look at local galaxies, what we can see is that the infrared SCD is telling you something about the way star formation is taking place in galaxies. If you compare one of those mergers, one of those U-lurgs, you have this infrared SCD, which is here in red, which is very different from the one in green that you have from a normal star-forming galaxy with a very strong pH features. In fact, you have a very different ratio of the robust emission from the robust dust, making the dust continuum, over broadline emissions from pHs which are easily destroyed by hard radiation field or compact star-forming regions. And you can see that the ratio, if you normalize this emission here, where you are dominated by pHs to the far infrared, you can see that most galaxies in the local universe have the same ratio of LIR over L8, which I will call the IR8 index, while the mergers have a very different ratio, this tail here with very high values, which shows that there is a deficit of 8 micron. And that is seen here, where you see that all U-lurgs and lurgs have this different behavior to the other ones. They have the same ratio here, and then the lurgs or U-lurgs are here. We're expecting that going to the distant universe, we would populate, because the rising population of U-lurgs is extremely fast, we would populate enormously this part and then decrease this part. But in fact, what we see by looking at the distant universe with the Herschel data, you have here the good north and good south fields, for which we have the deepest data and for which we have a nearly complete information on the spectroscopy of galaxies down to very deep magnitudes. I will actually work in mass selections in the coming slides. We can see that the distribution of this index is exactly the same for the distant galaxies as for the local ones, which is not at all what we were expecting. We are populating here the exact extension of the normal star-forming galaxies. So what we are seeing here is something similar to the main sequence in star formation versus stellar mass, which means that most distant galaxies, even those which form stars at rates of 50, 100, 200 solar masses per year, are normal star-forming galaxies with the same ACDs than the other ones, showing that the way star formation is taking place in those galaxies is more a scaled-up version of the other galaxies and very different from the local Eulers, which are extreme cases. A way to understand that could be just the ratio of 2D over 3D emission. So in a galaxy, you have an H2 region where you have ionization of the gas by the young stellar population, and then you have the warm dust continuum, a transition zone where you have the photodissociation regions with pH emission, and then warm, cool dust component. Here, if you just take these regions, subdivided like that, and then you make a more compact star-forming regions in a merger by not changing at all the distribution, but just making it more compact, you will have, by just this geometrical effect of more compactness, you will have a change of the IR-H ratio, which is about the same than the one we are seeing here. So it could be just a geometrical effect. And when we look indeed at the sizes in the radio of these galaxies, they are shown here with the blue histogram, and they are more compact than those galaxies which have a more extended star formation. And indeed, when you look at the projected infrared luminosity, you see that the compact galaxies have an excess IR-H versus extended star formation. So we can see from the infrared the probe of the way stars are being formed in the galaxies, and we have most star formation in galaxies taking place in those main sequence. Now it's an infrared version of the main sequence, which in fact can be seen as one single broad ACD, which is an average ACD. Of course, galaxies have very different ACDs, but when you combine the information from Herschel and the K correction, you can use broadband information to have an idea of the broad ACD, and these kind of ACDs have been found to represent relatively well the typical properties of galaxies. So you have three sides of the main sequence, the one which is now well known with the star formation rate versus stellar mass correlation, where galaxies above that are the starbursts. You have the Schmidt-Kenniket relation, but this double version that we heard about this morning. And then you have the infrared. Linda was mentioning her new results on these two star formation efficiencies. Here it's the specific star formation rate, which measures the starburstiness. And here we have an idea of the compactness of the star formation from this infrared index. Now, let me show you this main sequence with more objects. Here, I think it's 1,456 objects. You have a main sequence here as a function of the mass, and you see the starbursts are here. I forgot to tell you which objects they are. So it's animals. And here, what you have here is the longevity of animals. More massive animals live longer than low mass animals. And one way to see that is typically any animal has about 1 billion heartbeats. And of course, you have starbursts. All the birds are above. They are the starbursts. So why? I was wondering if it's because they fly or because they sing. But in the paper that I've read by those people here, they were suggesting more complex explanations, so I won't go into the details. But I just want to tell you that the same way an elephant is different from a squirrel, you can see very different morphologies for your galaxies. So what is it telling us? It's telling us that what we are probing here is something taking place at the very small scales. And when you look at the big scales where you see differences between animals, then these scaling laws are not telling you anything about that. So studying morphology of galaxies to understand that is not necessarily the best way. So what is the local information that you're gaining by this kind of scaling laws on galaxies? And there are very nice results which have been obtained recently with Herschel looking at the inside of galaxies. In fact, in animals, typically when you have 1 kilogram of flesh, it will consume a given volume of oxygen until it will have produced too much pollutants that will kill the material. and now free radicals. Now, what you can see here is on the top is the Polaris complex in the Milky Way, and you see this filamentary structure, and that's the places where stars are found to be formed. But in this place, there is no star formation, actually. What you can see is that the polar spectrum of this region is really typical of the turbulent cascade, and turbulence is preventing star formation from taking place in this region. Now, if you look at this HiPACC complex in the Milky Way, you also have filaments, but which are denser. And in fact, you don't go dense enough here to form stars, but when you go more above 2 × 10⁴ particles per cubic centimeter, then you have star formation taking place. And the very impressive aspect of this star formation found with Herschel is that the width of the filaments is universal, about 0.1 parsec. So you have a universality at the scale of 0.1 parsec, which is reflecting this universality of star formation in galaxies, which may need to invoke magnetic fields, because even with the kind of dynamics we understand in star forming regions, you cannot have this narrow distribution. And now I want to extend this comparison and try to connect all the scales. And what you can see here is that the ratio at which stars are formed as a function of the dense gas mass at scales of a few parsecs, 100 parsecs, and kiloparsecs are very similar. Now, if you look at the few parsec scales, about 15% of the dense molecular gas, above 2 × 10⁴ cubic particles per cubic centimeter, are in the form of prestellar cores in the filaments. And what is seen is about 30% of the mass in those prestellar cores are forming stars within a million years. So that means that you have about 4.5 × 10⁸ times the mass of dense gas, which is forming stars per solar masses per year. Now, at the 500 parsec scales, the study by Lada et al. Shows that you have a ratio of the two of 4.6 × 10⁻⁸. So the efficiency, the star formation sense, the efficiency of converting the dense gas into stars is about the same. And if you now go at the kiloparsec scales, you have the work by Gao and Solomon, where you probe this dense gas from the HEN molecule, and the factor is very similar. Well, 1.8 versus 4.5, I would say it's similar, and you have to determine there is uncertainties on the alpha HCl factor. So I would say that there is a quite universal star formation taking place once you have the dense gas. So one very naive way to see that is, even though the star formation history, the processes that are involved in star formation in galaxies are ranging from megaparsec to subparsec scales and very complex with feedback and everything, there is a sort of line of amnesia which is such that if you go below a certain scale or above a given density, matter forgets its origins and forms stars universally. So what you want to understand is what's happening above that makes the difference between galaxies. You want to understand why an elephant is different from a squirrel. So for that, we want to study the different behaviors, for example, of galaxies which are on the main sequence in the infrared or in the starburstiness, for example. It may not be that a galaxy which is on one is also in the other. In fact, in the local universe, you can see that the excess specific star formation rate is very well correlated with the excess IR8 that I showed before, and it's the same for distant galaxies. But you do have a big dispersion, and you have many objects which are outside this relation. So maybe we are not exactly probing the same exact thing. And this is a very preliminary analysis based on the morphological analysis of galaxies from the candles images. And what you can see here is that on the right side, galaxies which have an excess specific star formation rate, so the starburst, don't show an obvious signature in terms of their morphology. The birds. While if you look at the IR8 index, there is a clear rise of the mergers and a clear drop of the disks. So maybe what you can see from an eyeballing analysis of the morphology of galaxies is more correlated with the compactness of the star formation that you see in IR8, and maybe there are more mergers here than what we can see because maybe it's a later stage of the merger, but at least what we can see here is that the situation is more complex than what we would expect. We would expect the two to be exactly the same. So the main sequence is not telling us the whole story. We have to really understand the differences between these objects. So to do that, we are now investigating nearly all the Candles fields with Herschel data, the same depth than the Goods data. Now we have the UDS and the Cosmos field. We didn't get the EGS field, unfortunately, because it was not accessible to ALMA. I'm going to show you now a few results obtained by my PhD student, Corentin Schreiber, in a paper in preparation. What you can see here is the detections here of the main sequence at redshift 0.2, 0.7, 0.1, and 1.3. And to get the normalization of the main sequence, we're using stacking. while the dispersion is measured from individual detections. And typically, we don't see any evidence for a change of the slope of the main sequence, which is about 0.8, and the width doesn't seem to change. So we can split galaxies into starburst here and main sequence galaxies, and you have here you can see the starbursts seem to be more compact than the main sequence galaxies. Now, indeed, they are more compact, but you have to take into account the fact that galaxies are smaller if they have a lower mass. So what we did is we stacked galaxies as a function of their mass, and we selected star-forming galaxies from the UVJ diagram. And what we find is that at a given redshift, the more massive a galaxy is, the more extended it is. And then as a function of redshift, galaxies seem to be a bit smaller. I'm working here at always 2,700 UV rest frame, because I'm going to try to study the distribution of young stars in the galaxies. Now, if I look at the difference between the effective radii of main sequence and starburst, you see the starbursts are more compact. But if I take into account the natural differences with stellar mass and I normalize this relation, I find that there is no clear trend. So in fact, we don't find this evidence. We wanted to see, because that would have allowed us to correct for the excess extinction we see in starburst using the size in the UV. And instead, when we use the IR8 index, we do see a difference of compactness. So this is a better tracer of what's happening in the galaxies than the specific star formation rate. Now, in terms of the UV, what we can see here is that galaxies which have actually, I should start, sorry. Galaxies for which you determine the star formation rate from the UV correcting for extinction using the beta slope or the ACD fit have a very good agreement with the actual total star formation rate around redshift 1.3, 1.7. But then when you go at redshifts below 1, the star formation rate is overestimated when you use the UV corrected for extinction and underestimated above redshift 2. Instead, when you use the stellar mass, you can see that there is no change or very little change of the ratio of the infrared over UV star formation rate as measured by this AUV here at all redshifts as a function of stellar mass. So here also, the stellar mass is the best proxy of the attenuation in galaxies for the main sequence galaxies. But now if you look at the starburst galaxies, I'm showing here the Rodiguero et al. Paper where you have the star formation rate versus stellar mass redshift 2. The starbursts were detected from the infrared, while most of the main sequence galaxies are coming from the UV corrected for extinction. And what you can see in this diagram here is that excess specific star formation rates, so galaxies which are starbursting, also show an excess star formation rate in the infrared over UV corrected for extinction. So that means that you will systematically underestimate the star formation rate of starburst. As a result, if you want to study the effect of environment on star formation in galaxies, and you use a technique which is based on the stellar mass to estimate the correction for extinction, you will erase completely the starburstiness. And that's what has been seen in this paper by Koyama et al. They had initially what they find is that as a function of the local density of galaxies, the specific star formation rate as measured from H alpha and corrected with standard recipes doesn't show any trend. But if you correct, if you use the infrared, you can clearly see that there is a rise here. And in fact, the attenuation in H alpha does rise with the density, and it's because in the denser regions you have more compact star formation and there is an excess obscuration. So it's clearly a key issue here. To finish, I want to mention the results that Linda mentioned before, which is the fact that you can use the integrated infrared light to measure the dust mass of galaxies. And this dust mass can be converted into a gas mass once you know the gas to dust ratio, and that you can determine it from the metallicity of galaxies. I don't enter into the details, but using this technique, you can measure the gas mass of galaxies, compare that to what has been done using the CO measurements, and as Linda was saying, it's extremely consistent. You can see here that the gas to dust ratio is decreasing with metallicity, so that is taken into account here, and you can measure with thousands of galaxies the typical gas fraction in galaxies. That's the work of McDis et al. 2012 from redshift 0 to 2. And clearly, this is very consistent with the alpha CO that Linda was mentioning before, in the sense that main sequence galaxies have a higher value than the starburst galaxies. And it's not Eulers that are different, but it's starbursts. Using this technique and the two modes of star formation, the main sequence one and the starburst one, which we call the two star formation mode approach, we have been able to get a various series of results that I just mentioned here. You can fit the infrared luminosity function evolution at all redshifts with this simple approach, and it's giving a better field than most analyses that have been done before. You can fit number counts at all wavelengths in the infrared. You can follow the cosmic evolution of H2, and the bulk of the cosmic evolution of star formation appears to come from the gas fraction. So I let you leave you with these conclusions. We see a universal star formation mode that dominates the growth of galaxies. But one thing to keep in mind is that this is hiding differences between objects, the same way an elephant is different from a squirrel. And indeed, galaxies above redshift 2 in the main sequence have a typical formation, doubling stellar mass, timescale lower than 500 million years. So that means that galaxies forming their stars here have the typical timescales of bulges, while those forming their stars here have the typical timescales of disks. So main sequence galaxies are forming both bulges and disks, and they are very different populations. Thank you.
Questions? Are you worried that in this study where you're looking at the sizes of these galaxies, you're using the red frame UV for presumably very vastly obscure galaxies? Are you considering trying to extend this to the optical to see?
So yes, we have looked also at the optical. The reason why we're using UV is because we want to see the regions where the stars are formed. So in the optical, there is no obvious signature, but we are trying to compare the two, but it's less obvious. Now we have obtained ALMA time to study the sizes in the submillimeter of galaxies, and the observations have not yet been done. So we have about 28 galaxies at redshift 2 coming that will be done in the fall.
Do you worry that expanding the selection from the main sequence looking for a starburst galaxy, perhaps some of them maybe even drop the red images, some of them maybe completely obscure during those?
So we are selecting objects here from the mass, stellar mass, and then stacking objects independently of their.
Any more questions? Okay, let's thank David again.